Hi, that's Peter Turbine. It's John Wanoa here in Auckland, New Zealand. Just send you this little short clip late at night. It's 11:45 p.m. Just a little bit tired, but I just thought I'd just send you a little clip just to let you know what I'm doing here. We're wanting to look at plans to design and build as a consultant for us, Moai Powerhouse Group, build the tidal turbine, Moai Tidal Turbine, in the seabed, over 100 metres below, and the strongest currents in the northern hemisphere, or in this case South Korea, where your Cowi Korea Company Limited is set up after designing and you designed and built the tunnel, Busan tunnel to Gorgie Island, 48 metres under the seabed. So it suits us to have the turbine built in South Korea in the workshops there, since it's all there in the pontoons and all the steel and all the equipment that can go into building the turbine, and the generators probably have to come from Switzerland, and there's the hydrogen compressors. So there's quite a bit of work to go into it, and bringing the engineers together. Similar, it's not as hard as what you've done with the tunnels. It was a bit more precise that, but the turbine is inside a 32 metre cube of 3 metre diameter pipes that are welded into the frame, and inside that the turbine spins. It's on a T, a 3 metre T, a shaft going up, and goes sideways and goes the other way, one piece, and then the blades are pivoting on those shafts that way. Large blades, they're 25 metre to the outside diameter, 12.5 metre radius, and 25 metre high, and so that's spinning around slowly. All we're doing with it is the vertical blade, like that, okay, on one side, going downstream, and we drop them onto the ridge. We'll find a spot. I think you've got a submarine there. It takes 9 people. You can go down and tie it and anchor it at the bottom and find where the currents are around the coastline of South Korea. It'd be good to test it there, because out of the shipping lanes right into the deep, it's too shallow in the inner harbours, and you'll have a lot of protests there. They're already having protests over the other tidal energy project, which doesn't appeal anymore, where they dam it up and then let the tide run through the turbines. And we don't do that. We use sea currents. The current going in the best place over there, I'll just forget what it is, but anyway, we've got it marked out on the map. You'll see it on some of the stuff I send, where the current is 6 metres a second, so going that way, 6 metres. So all we're going to do is put the blade that way going downstream and stall it to 1 metre a second distance, 1 metre a second. So that's going to take a lot of ton force to hold back, to stall the shaft going around, right? And the shaft, and on the other side, on the upstream, when the blade comes back on the other side, it goes on an angle that's comes back like that, it spins like that, but it comes up 45 degrees 45-degree angle. It comes around 45 degrees halfway, and then it goes back the other way 45 degrees. So it lifts up the thing for for 45 degrees, and then it drops it, pushes the 3-meter pipe the other way down. So you've got a 3-meter piston up the top and a 3-meter piston hydraulic. The water, so you've got a water bearing up the top and one at the bottom. And so the pressure we get from that we put through the pipe out to the ends around the edge of the turbine to throw it around. So that's just to give you an idea of how we're going to capture the force of the tide moving in a block of water. So you've got 5 meters of thickness that way forward on the downstream, and you've got 12.5 meters that way and 25 meters high, all that cube of water tonnage moving that way, and all you're going to do is stop it from going, and instead of taking 5 meters a second, you're only going to go 1 meter, and you've captured all that power in hydraulics. We use hydraulic power of the pumps. And the other thing we do to stall it, all we do is when it's free spinning, it's going, the blade will go around faster, only as fast as 5 meters a second. So a log going down a river is only going to do 5 meters a second. So the turbine blade will only turn slowly at 5 meters a second round. So what we're going to do is load the shaft so that it's actually going to slow it down with loading it up with compressors. It would take 20 300-ton compressors to actually slow it down to 1 meter a second. Right? That's including the pump at the top and the bottom to give us the water pressure, right? Water pressure, and also that's a water bearing to keep it central. And because the blade is going that way, the 10,000 tons on that side and the 10,000 tons on this side, by lifting it, you've got the 10,000 tons on the piston going up and spin down to go down that way. This is floating, ballasted. Okay, so when it's sitting in the water, it's floating in the middle. So when it goes up, it lifts it up like that, and it'll naturally come back down. But the force of the water going forward goes up against the blade and pushes it up, and then goes down the other way. Okay, so that's how we get the power, just to give you an idea of this turbine. I'm just drawing it up at the moment. I'll send it tomorrow, and you can see what I mean, and it'll turn all right. I'll guarantee it'll turn. The only thing now is the engineers and their generators and everybody fits them around the shaft. I'm going to put a cam on the top, and so it'll a 4 square cam that it slides in the thing at the top and the bottom. So it's got a cam up there that pushes the pistons, the compressors that way. So you can just pull them out and load and keep loading it up on the stroke of the pistons around the shaft, around the cam, a 4-place cam that's going right out at least 10 meter stroke, right? A 10 meter stroke of the pistons up right up the top and right at the bottom. You've got hydraulics of the compressors that are compressing hydrogen. You've got a big piston. You might have a 3-meter piston to start with, and you've got a 2-meter piston, a 1-meter piston, and then half-meter piston, so that you get the pressure right up to get the liquid hydrogen. We're going to use the generators. It's better to build them, design them bigger, compressor, because you don't need all the fancy stuff. You just need a cylinder and a solid metal piston in the middle to rub up against the cam, and a spring inside it, and the valves on it. That's all. Because it doesn't need lots of little ones. You just need one big one. Because it's the mass amount of power. It's 1,530 megawatts. It's going to come out of that shaft. And what happens is, in some places like New Zealand, the tide goes around one way. Chile goes from New Zealand to Chile, or goes to Tahiti, Chile, and up to Hawaii, and across to Tonga, Samoa, and down to Australia and back here. So just one way, and you can get the the turbine won't stop. This turbine is not going to stop whether the tide goes that way or the other way, because what happens is when the pressure drops, when the water pressure drops, the jet engines on the end, the reaction engines, jet engines, they're on the end of the turbine, right? And when the water pressure at the top and the bottom shaft goes through the middle shaft of the shaft, it goes out the cross shafts, right? It goes out the cross shafts, and then it pushes the water, forces the turbine around, and then this jet engine's in the middle of it, up the front here, and it's burning the stored liquid hydrogen and liquid oxygen that we store in 20-ton tanks, right? Why 20 tons? Is that we're going to use them as like torpedoes under the water, and it doesn't matter how far you're out, 100 kilometres away. We've got jet engines to go on the side of them to push them back to the shore and put the empty bottle on and go back out again. No wires, no cables, no pylons, no trucks to cart things. It's all going to be done by helicopter. The Russian Mi-26 helicopters that we've got sitting in Russia, we can get some of those. And so they'll be picking up from the shore, where we have a place right out of the way, and pick them up and drop them at the power station, substations, the airports for the planes, the truck stops for the trucks, and the cars can fill up from this one big tank. So it's going to be, they'll be burning it off as fast as the turbine to keep up, and the bottles will be going backwards and forwards to keep up with the turbine, because it's going to spin it out. It should cost $1 billion to build, the first one, but its turnover, I've worked it out to $5 billion a year, turnover in liquid hydrogen jet fuel. Okay? It's a massive amount of fuel made from splitting seawater with the electricity, and we're only going to use as much electricity as it will take to electrolyse the water. All the rest of the power will be used up in the hydraulics of the forcing out the end of the turbines, and also the stalling power of the hydrogen compressors. It will take a lot of the power out of the shaft and harnessed out of the water. So that can be portioned out, but the engineers can work it out. My amount of engineering, I'm a mechanic engineer that designed this thing over a period of time, and we're going to use local material in those countries where we give a license to build them. And so they, in Denmark, they can use their own expertise and their own generators. Like Germany will use their own generators, whereas Cowi will use their own generators. And the compressors come from Switzerland, the big 300-ton ones. So they can use their own, or somebody can build them and save a lot of money and a lot of the fiddly little things we don't need in this design. Okay, so everything's simple, and it shouldn't need. I think even the generator poles on the end of the turbines will produce enough power to electrolyse without putting lots of little generators around the place. We put big poles on the end of the turbine blades to produce just enough power to electrolyse the water to turn it into oxygen and hydrogen. So all these things are in the framework, and it's got buildings under the water too. So we have a cube, and then we've got 4 poles on the outside, 3-metre leads that go right up to the surface, and so we can ballast the whole turbine to get them out of the water, and everything will assemble itself by floating out and dropping down, base on the bottom of the seabed, and the caissons into the seabed, anchor. I've got a way of anchoring it, I'll draw it up, and then the turbine will come down, the cube come down and bolt on. The legs on the outside of it go up out of the water, and the building outside of the, and then that's That's going up to 32 meters cube. That's the unit itself with a generator. And outside of that, it's 40 square, 44 3-meter pipes going all the way up to the surface, and then the turbines go up that, and then they lift up out of the water to service them. But it's going to take a long time to service because you've got water bearings, and it's only turning very slow, and the compressors are only going that slow. They're not going very fast. Everything's going slow, so you can't get fish getting tangled up in fast-moving blades. No. But you've got the jet units on the end, which is going to throw submarines or anything out of the way anyway, because there's a big force coming off right around as the blade goes around. The jet engines. When the tide slows down, the jet engines rev up and burn the fuel we're storing. So that's to give it to you in a nutshell, Lars Peters. You can get a general idea of one of these things that can put out 1530 megawatts. The 4 reaction engines, that's the name of them, they're going to put them in the hydrogen Lapcat, British Lapcat A3, and that's what we're chasing after, to refuel those planes and make them fly, because they're on the drawing boards in the European Union Commission, but no fuel. They've got nowhere to fill them. This is the answer to fill those planes, is this turbine. Right? It's putting a massive power. What happens is the legs that come up will form the cantilever bridge, right? And the next one will be 500 meters away. And we put another turbine over there, and so we put the legs up again, and then another 500 back the other way. So you've got 1,000. You've got a kilometre of runway on the top, and multi-story buildings sitting on the top of this turbine unit, and the turbines lift right out of the water underneath the bridge and screws on, and then the platform there to dismantle them. Right, it's quite straightforward, and the tanks are stored underneath the ocean. They're stacked up like that, and that forms the, we put them out, it's like the square, and then you've got these tanks stored like this, so when the water comes in, you double up the speed. So with the speed 6 meters a second, and you've got this row of tanks. These are storing, they'll be 32 meters high, right, the height of the turbine, and a bit more for the ramp at the bottom. So we're going to speed the water up going through by having this, you've got the square here like this, and these off like that, like that, and the water comes in like a V, and because it's the same distance, another 32 meters, it's going to come, that speed of the water going through the turbine now is going to increase from 6 meters a second to up to 25 meters a second. So you're going to get more oomph from the same thing. That's what I'm saying. There's a lot of power in it when you speed the water up coming through that way. So you're getting double the amount of water on that side and double the amount of water on this side going through this turbine, and you've got a ramp coming up like that because you've got the building underneath, and then the thing sitting on top of the seabed. It's not going to sink under the seabed, it's going to sit on the seabed. So you've got at least 4 meters of building underneath. That's all the compressors and everything, right? And then you've got the turbine, and you've got another building up the top. So you've got a ramp coming up, and the water's going to speed right up that way, and it's going to speed that way and this way. And when the tide turns around the other way, it's on the other side too. It's come back the same way. And at the top, what we have at the top is we've got the ramp that way, and the water's going to go up that way at the top, but straight through. It'll slow down going up that way, but it'll push the force to hold the whole thing down, right? And on the other side, so that'll push the turbine into the seabed so it won't lift up. And the force of everything around it I've designed so that it's anchored to the seabed and won't move. Okay, but we prefer to go into rock than sand. Okay, so that's supposed to be a short video, but I just thought I'd give you a good explanation of it. And we're anxious to get it built. And well, it'd be nice to put it in Nova Scotia because I'd love to see it churning out the power in those tides up that way. In Ireland, where they got the windmill thing, it doesn't work like those C-gen turbines or those other flimsy paddles, windmills. We've got giant paddles that actually got bigger area, right? And trying to stop the sea with a big concrete steel wall. It's hollow, it floats, it's ballasted, and it's variable on the pitch, right? Everything's hydraulic. Everything's hydraulic with the pressure that we get from the top and the bottom of the shaft. That's going up and down like that, okay? So pressure at the bottom, pressure at the bottom, pressure at the top. So with all the hydraulics and everything, and everything works by that and sensitive. It's pressure sensitive. In fact, no computer to muck up or stop. It's just straight pressure. Okay, and apart from the current, we get this low voltage and high amps. So there's no radiation for the fish because we don't have high frequency. Right? It's just low volts and high amps, the power to electrolyze the water into gas, oxygen, and gas, hydrogen. You've seen the bubbles inside a thing when you put a battery onto the water, it'll start bubbling while there's oxygen and hydrogen coming off. We just compress it and put it in a bottle. That's it. And we have technology from HB Technologies from Taiwan. They got solid metal hydrogen fuel storage systems. So we're going to use that in the next project. We've got a pending contract with them to supply their tanks, but they can build tanks to bigger ones because we need big ones to store more fuel in metal. And so that's going to be a plus. So we'll just leave that one until we get what it looks like under the water first. So that's me from Auckland, New Zealand, just explaining something to you, Las Peters and Christina. Thank you for talking to me tonight, 24th. It's just flipped over midnight now. Should be asleep. And look forward to getting your answer on this. And the good thing about it is that it's the first at that depth to go and get the power, the hydraulic power out of the sea, and there's plenty of it. And a good measure of superconducting magnets can be used, and this bulk power can be taken out of the shaft on the brake horsepower. And being a hydraulics mechanic myself, it's totally different to the other systems of making power from windmills. They don't actually get all the torque out of the medium they're using, whether it be hydro dams. They've got a lot of power loss and a lot more space. We're only getting, I'll tell you this much, we're getting 1530 megawatts of power from 32 cubic meters of marine space. Now work that out. That's a square of 32 meters that way, and that way, and you're getting that much power. That's 1,320 windmills spread all over the countryside, right? That many 1 megawatt windmills making lots of noise out in the open and going fast and wearing out quick. This thing doesn't wear out for a long time because it's very slow. Anything that turns slow don't wear out in a hurry. Very powerful for the space. 32 meters. The rest is just the bracing that takes up all the room and the tanks at the bottom. So you've got like square, and the tanks are 32 meters long, going that way 45 degrees, and going this way 45 degrees from the corner of the outside square, a square inside a square. The cube is inside, and it slides up and down inside the inside pipes. And the outside pipes, where these tanks are going out the way to store the fuel that we use when the tide's stopped to turn the other way. The jet engines are going full bore, right? 1,500 megawatts of power comes out of the 4 jet engines to spin the turbine around to keep the pressure of the water pump going, and the generators. Okay, never stops at all. 365 days a year, goes on forever. Thank you very much. We'll see you later, and I hope we can get onto this. How we finance it is we've got shares running soon. Oh, it's already started for raising the money for the project. I've just been talking to, I emailed to Ban Ki-moon in the United Nations. We've got something to do with them, and to encourage them to look at it, and also interested in the companies coming in to build it, putting shares in for life. Right? The shares are for life, not on the stock market. We're just going to keep this one because it's guaranteed itself, and I'm that confident that if we sell one share for £20, that's what it is, £20 share, you get a free one. Okay, there's 1 billion shares going out on our website, and so that should raise 20 billion pounds. Everything's in pounds, and we're going to operate from London, and hopefully we can come and see all this go together with Cowi. Looking forward to it. Pretty well up to it on hydrogen and mechanics, and how things work as an engineer mechanic with this power project. Okay, thank you very much. I'll see you later. Bye for now.